Okay. Yeah. Some quick news. I got the PPO. Yeah. That's the first thing, of course. Yeah. So all of you know, I was doing this internship at Texas Instruments, and so they offered me a 3%. I mean, they are going to offer. It's like they're confirmed that they're going to do that. I don't really care, frankly. Like at this point, I just want to get done with stuff. Like, you know, build a career, not just a job. uh, yeah. Anyway, so what am I doing right now? Well, one thing I really just want you all to know, I'm taking some really messed up courses this semester. So there's this one course which like I'm suffering with. It's cognitive psychology. And you might be thinking, why am I doing this? I'm from BTech. I'm not supposed to be doing any of this. Well, sucks to be you. Can't think out of their boxes. But yeah, so I'm taking a bunch of courses which I probably shouldn't be taking, like as just an undergraduate, right? You got this course which I picked for the humanities basket. This one, which is once again just humanities basket. They're going to teach Blender and all that. This was a project course, but then I never really did this. This is, I don't know why this is there. This is from last semester. Yeah. And then I'm taking biostatistics. So this is still like relevant to what undergraduate stuff is, but not exactly computer science. So this is going to be more about like clinical trials and all that sort of stuff. So it's like if I want to get into that field at any point of my life. But frankly, I'm just taking this because there's a lot of statistics inside this. They're starting off a little slow, but I'm sure we'll reach there someday. Okay, now enough with all that. Let's get to the meat of the video. So computer networks, I'm just going to run you with a very, very brief sort of introduction before I even get into reading all that. So this is going to be like a very long video where I just read stuff and note it down, and maybe I like run a few terminal commands or Google what this thing really is. But yeah, more or less it's just going to be that, like a recap plus a walkthrough of taking notes or something like that. Just a disclaimer, my typing speed is really bad, so yeah. But let's get started. So chapter 1, of course. Chapter 1 starts, this is a top down approach, by the way. So for all the layers that you'll have, you'll be going from the top layer, that is like layer 5 application layer, all the way till layer 1 physical layer. Okay, so what's the internet? This is like a bunch of bullshit that they've written in the book, but frankly the internet is just like defined in two different ways. One, you can think of it as an infrastructure that is like similar to an operating system. You would think of it like that, right? Where you do system calls. Similarly for internet, you do, I don't know, internet calls. Really, it's called API, but yeah. So basically think of it as a tool in your toolkit. That's one thing. It's a big infrastructure which allows all that, like people to communicate. Also, you can think of the internet just basically as a network. Like you think of the parts themselves and how they are connected, and that basically is the internet. So in one, its internet is a faculty. In one, internet is what we do, as in we as a big network do, right? Yeah, I mean it's actually scarily similar to a brain, but yeah, whatever. That's just two ways. Don't really care about that. So early internet devices were very limited, but nowadays you have an internet of things, so you can connect anything, even thermometers, even your toilet seat. I don't know who would want to do that, but you can connect anything to the internet. Just some terminology, the devices that you'll connect are called hosts or end systems. So even servers are called end systems. Basically anything that does the computation, right, is the end system. So here's where you can think of the internet as a distributed system. So if let's say you are playing a game, right, it's a multiplayer game and it's being played on, I don't know, 3 devices, right? I don't know what sort of game this is. Maybe it's just truth and dare, so on some online platform, right? So what will happen is that it's like the computation is done on your devices, but then the communication is done through the internet. Yeah, but you can think of like internet extending to your devices as well. And so you just say, okay, the internet is basically providing us these applications which run distributed and not on a single device. Right, it's just some statistics. In 2015 there were 3.2 10 to the power 9 hosts, and power 9 is like a billion. So there were billions of hosts, which is like around 40% of world population. Now it must have been much more. And systems are like linked by communication links and packet switches. This is going to be important when we actually get into the meat of how like packets are sent and all that. Yeah, communication links can be made of multiple things. They can be made of like coaxial cables, which is like you have a rod like conductor, not a rod exactly, but like a let's just call it a rod. Like if you just take a what is it called, just like a cut of the thing. I think it is even called something, right? I don't remember. Yeah. Okay. Wow. Anyway, so you just take a cut of the thing, then you'll see that inside there's like a rod, and then there's some insulation on top of that, and then on top of that there's a sheath which is also going to conduct. So both the rod and sheath conduct, except that they have the electricity going in different directions. So then by Ampere's law, your Ampere's law or some law like that, I don't remember, it's something like integration of magnetic field over the, so like the circulation of that is like mu times of the current. Yeah, that thing. So by that, since the total current going through the circle is like 0, so the magnetic field just becomes 0. So that's a good thing for the coaxial cable. We of course have things like normal twisted copper wires, which also give like 0 magnetic current, except that they're like twisted rather than coaxial. Yeah, they're like DNA strands, if that makes any sense. Frankly, there are going to be like multiple different strands, and all of them will be twisted. And it takes quite a bit of time to create something like that, because then you actually have to twist it. So it's more costly than just like a coaxial cable. But yeah, those are there, copper wires, just twisted copper wires. Then there's obviously optical fibers, because come on, the whole internet runs on optical fibers, right? When you want to communicate between continents, that's the way to do it. So you got optical fibers, which requires like its own whole machinery, like optical splitting and routers and all sort of weird stuff. But yeah, there's that. And then there's the like there's just like radio frequencies or some other frequency, right? So you have usually it's the radio frequency, because it's harmless. At the same time, we can't really see it. Like imagine things being communicated through like literal visible light, like you're sending yellow pulses out into the sky or something. That would be very weird. So you got that, of course, and that's used for things like Wi-Fi or satellite links and these things. In fact, there's a bit of an issue with it, because like it's a shared medium, so you can even do things like packet sniffing. Yeah, I mean you can do it with wires as well, because like in the end you still have data flowing through it. But yeah, here it just becomes easy because no one's gonna detect it. Like the packet sniffer could be very small and then no one detects it, so you're doing some illegal activity, but like it's hard to figure it out. And packet sniffers usually are passive devices. They just like get the thing without really sending anything into the internet, into the medium, that is. Yeah. So just to recap, they can be made of coaxial cables, twisted copper wires, optical fiber, or radio spectrum. Alright, transmission rate of a link, it's measured in bits per second. Similar to transmission rate, there's something called as, actually you know what, we'll get to that later. Let's go to say like traffic ratio, is it called? Intensity, yeah, traffic intensity, but we'll get to that later. Okay, so how does transmission really happen? So when the sending agent A, it wants to send some information to receiving agent B, it will first segment the data. So like you know, your application layer messages are literally segmented into data segments, and it adds some header bytes to each segment, and then each segment is now a packet. That's it. It's like it's encapsulated. It contains all the information of the previous unit. So the previous unit is called the service data unit, which is like the message that you wanted to send, and each segment is called the protocol data unit. So for each layer you'll have some protocol, so whatever that layer produces as its packets, as the packets for the next layer, I think. But yeah, those will be the protocol data units. We'll get to all that, but sure. Okay, that's that. The packets are reassembled into the original data at B. So there's something known as the I think it's called the layering principle, where whatever data you send at a particular layer, all of that will be available exactly the same way on the same layer in the application in the receiver's end. Right. Yeah, so there's no loss of information. I mean, there is loss of information at times, like think of UDP, it has loss of information, but for something like TCP you don't have that. You can expect reliable data transfer. Okay, let's get to some more terminology. What's a packet switch? A packet switch is basically like, it takes packets from one end or many ends in fact, and then it figures out where to send it, and so it switches. This can be a passive device, and this can also be an active device. So when it's passive, it's usually called like a communication, so I think a link layer packet switch. It might even be active, frankly. A link layer packet switch can actually be active. But when it's active, it's usually a router. So routers work by a store and transmit principle, which we'll get to. But yeah, just remember, like, packet switches basically are like these decision nodes. Yeah. Okay, major types of packet switches: routers, link layer switches. So this is used in access networks, and they can be active, passive, whatever, but like so far what I've seen is usually just passive. You have like multiplexers and optical splitters. Yeah, I don't know. And then you have routers. So routers are very intelligent like entities. They run up to the third layer protocols. So the third layer being the network layer, right? You have like the application layer, the transport layer, the network layer. We'll get to all that, but yeah, just remember they're kind of intelligent compared to just passive switches, link layer switches. They're way more intelligent. Okay, now of course a router is basically something that creates a route, right? So a route or a path. So let's say you have A, which is a sending system. It's sending some packets, and then first it encounters a packet switch. This packet switch can send something to C, but it does not because of obviously because A has addresses on each packet. So then packet switch sends the information to some other packet switch, and that sends it to some B system, which is the receiving end system. So this whole red path that you see, it's called, well, a path or a route. Yeah. And when this thing is an active agent, it's called, you guessed it, a router or a router or whatever. Okay, TCP, IP. So these are names of protocols, and TCP is the best known transport layer protocol. There are only two, by the way, in the transport layer. You have the UDP and the TCP. Yeah. So end systems, of course, run the TCP. They obviously also run the application layer protocols, but they run the TCP. And then the internet service providers, they usually run just the IP. They don't really care about managing all that. Usually, I would just have like a direct a TCP connection to like whatever, I don't know, server or device that you want to connect to, without really having to worry like what's happening underneath. So that underneath thing is just the IP protocol, and I haven't got to the IP protocol yet, by the way, because it's a top-down approach. So I only know till the TCP layer. I mean, not even the TCP layer, till, so just the application layer. Okay, and then you have these standards. So RFCs, they are called request for comments. Now you might be thinking, okay, why are these requests for comments? Well, they are just comments, frankly. They're basically like comments on how to like create a protocol or something like that. Like, what are the standards? So they really are comments and not like rules, more like guidelines. Yeah, like conventions basically. And it's called requests for comments because of the process in which these comments are processed. That was really bad. But yeah, there's a community, I think it's called something in engineering. Yeah, so internet engineering task. I'm not kidding. This is really like the name that was given to that entity. It's a task force. So yeah, these are the people who create these comments or standards. And the way this happens is a person will write a blog. Let's just call it a blog. More like, I don't know, it's more technical than that, but they'll write something. They'll send the write up to the engineering task force. They'll probably also send some demonstrations and all that, and maybe some mathematical calculation. I don't know what really they have to send. It's like a paper or something. Probably they'll write an associated paper as well. But yeah, so you do that. You send it to the IETF, and that thing is called a request. So it's a request for comments. Yeah, and once it's processed, it's put up as a standard, and it's still called a request for comment. I don't know why they don't remove it to just comment. but fine. So these RFCs, they were initially just like requests, but now they're coming. Okay, and these are quite detailed, and there are RFCs for almost everything that you see. So you have TCP, IP, HTTP, SMTP. Of course, these are like application layers. This is just like, okay, transport network, but yeah, it's there for everything. So by the way, in the application layer, you have all sorts of weird things going on. You have like web browsers, you have mail servers, you have like peer-to-peer communications like file transfers, FTP, and all that stuff. You have this POP3 thing, like an HTTP mail browsers. No, wait, Gmail. Yeah, but right. Okay. Also, the local area network, or what's MAN for? I don't remember, but it's like larger than LAN. So these standards, committee, IEEE standards. Okay. This specifies the Ethernet and Wi-Fi standards. I really don't want to get into any of that, but we'll of course get into what an Ethernet is, how does Wi-Fi operate, all that. But yeah, just keep going. So the services description. So far, yeah, we've only been describing like what are the parts and how do they operate, like the protocols and the different devices involved, all that. But what is like internet in an abstracted form where you can't really see the parts anymore? Then you just think of the internet as a tool, right? So what kind of services does the tool provide? Well, here's a bunch of applications. So it provides a lot, and it's kind of like, it's way too simple. Like email, for example, it's kind of a simple thing. Of course, not as simple as HTTP, but still, it's actually kind of a simple protocol, just the application layer, of course. And I'll get to it. I'll of course like get into it and tell you what it really is like. But really, like, these aren't that complicated as they look. Like, you could literally build a simple messaging application all by yourself. Yeah. Of course, we'll get to some slightly more complicated things like DNS, and then you start to appreciate the complexity. But yeah, so you have a bunch of applications. You have email, you have web surfing, messaging, mapping with real-time road traffic information. Yeah, so like Google Maps, all that. Music, movie, media streaming from cloud. That's once again just HTTP, but still, it is a service. Like, this is a very high-level view of the thing, where you just look at what things we can do with the internet, and not really at the core what we are doing. Social networks, Facebook, Instagram, whatever, LinkedIn, yeah. Video conferencing, you have Google Meet, Jitsi Meet, all these things, right? Real-time multi-person games. I mean, do I even need to tell you about this? Location-based recommendation system. So this is kind of just a mashup of the location and the social networking, but whatever. So each of these are used, like each of these are said to be distributed applications, since what's happening is that these applications don't just run on one device, they run on multiple devices. For example, if you just have a mail, it doesn't just run on the two devices that are trying to send the mail to each other. There's like a bunch of stuff that happens between. So there's these things known as like mail servers. So you'll at least have like, I don't know, okay, you might not have the root server, so you might have at least like 2 mail servers that the information will go to before it even reaches the end host. The receiving host, yeah. But then again, there are more complicated things like, I don't know, a multiplayer game. In that sort of scenario, you really have to think of these as being hosts, because they host the application. And then there are like extreme examples of just like P2P, for example, right? Just BitTorrent, something like that. There you don't even have a server. What do you do at that point? I mean, okay, you do have a server usually, but then again, that's not the only thing. So then really, like, the whole thing, your whole network is basically the computer, just like a brain. Yeah, so this is also why we call the end systems as hosts, because, well, they host the application. Okay, next thing, the sockets. So a socket is basically something that you use as an interface, like you as a programmer, when you want to communicate with some other device, what you'll usually do is you'll use a socket. So yeah, so this is a very sort of vague description of what a socket does. but really it's something like an I don't know. It's just like a big class. You can think of it like Python classes just have a very big object called a socket, which does a lot of different things. Yeah, you can just think of it like that. This is just some sort of abstraction, more or less. Okay, the protocol definition. Like, what is a protocol? So protocol just defines the format and order of messages exchanged between two or more communicating entities, as well as the actions taken on the transmission or receipt of a message. Okay, this is, yes, it's true, this is the definition, except parts of it applies to different protocols. Like some parts may not apply to HTTP, for example, some parts may not apply to SMTP. But yeah, in a sense, this is the thing. Like anything that follows all these rules is basically a protocol. Okay, and I don't think anyone really needs to remember this because we'll see a bunch of protocols first, and then we'll come back to this definition. Okay, so this is a very simple example. You're just browsing, right? Web browsing, and we'll study all that in detail when we get to HTTP. But yeah, so what happens is like, okay, you know what? I probably shouldn't be going through all that because there's some weird stuff that I've written. Okay, let's just get to the network edge. Yes. Okay, you know, let's not actually open any of this because I remember now I've written very weird stuff in this, which is like primarily meant for me to remember stuff, but it's not a good idea for you to see it. But yeah, so what's an edge? Let's think of it as a tree. Like, think of the internet as a very big tree. Okay, a tree is a bad idea, a very big graph of kind, right? So nodes that are not going to have any children nodes, right? Those are at the edge, and then maybe some layers deeper than that as well. You just call it the edge, right? But yeah, that's what the network edge is. That it's just the end systems basically, which are not like which are not really there so that they can facilitate communication. They are the people who want to communicate. So the question is, how do these get connected to all of internet? Well, that happens through an access network, and there are many different ways that you can have access. First is, okay, so before any of that, there's also this thing called the IoT. So okay, once again, why did I write all this weird stuff? But okay, the IoT is basically that instead of just having traditional devices like personal computers or laptops or these things attached to the internet, you can connect anything, right? Anything that anything that sends a signal, it's something you can connect to the internet. Okay, let's think of a few ways to do that. In the era that my parents started to use internet, what they used to have was internet directly through cable. So that's called cable access internet. So what happens is telecom like providers, people who would, not telecom, I don't think that's the correct word. Telecom is for telecommunication. So these people who used to give you cable TV access, right? They have this sort of infrastructure built in where what would happen is that they'll have something streamed into their offices, right? From outside. I don't know how they got it inside of it. Like it's some movie or something like that, right? And all of this data will be sent without any discrimination to everyone. So there's basically no routers or anything like that. What happens is all of this data is sent without discrimination to every single part in this access network. So you have these fiber nodes, so fiber cables are basically like very fast ways to get the data flowing. So you'll reach all of these fiber nodes, and from there there's like these slightly cheaper but slower cables which provide it to different homes, and homes would have TVs where your signals would be interpreted, and then you'll see some graphic on the television, right? That's how TV used to work. Now what can actually happen is that the people could also use this for streaming services. That is, if they have, so like on-demand streaming services, and not even that, they could literally use it for a lot of other stuff like files, downloading files and all that sort of stuff. So what would happen is that you would use the same infrastructure to have both a down and an up transfer of data. So now each home can send a packet which requests through whatever protocol, actually a series of packets which requests through the protocol to some other device on the internet. So this wasn't there, by the way. The internet wasn't used to be connected, but now this guy has connected it, your provider, and now he's not just your cable TV provider, he's also your internet service provider, because through this infrastructure you are sending up data packets and you're getting some response. So that's basically enough to have whatever protocol you want running, and this works well if you just have like one person attached in the whole access network, or if like people are so sure that they wouldn't be, no one else is going to like look at what you are doing, like what packets you're sending, what you're getting, it would work well, right? So you have now on demand streaming or on demand files being downloaded or something like that, or basically HTTP at least works. Yeah, so you can browse and all that, right? And this is kind of okay because at any given moment you're not going to be getting, so your browser isn't going to be like downloading thousands of different files. It's just going to be downloading one file, probably just the HTML page, right? And then maybe some images inside of it. So it would be kind of okay, frankly. This isn't like bad at all, except this sucks. The speed that this gives you is still very low. The main reason being that the infrastructure itself wasn't meant to be like supporting, you know, high speed communication. It was mainly a streaming service, right? Its main function is that your TV should work. It's not supposed to be that you can download files easily or things like that. So this isn't optimized for that, and so it kind of sucks, more or less. But yeah. Oh, and what's a CMTS? So the cable modem termination system. So once again, remember that you're basically sending analog signals over these wires, right? So the way this works, the way these signals are converted back to digital and so forth, that happens through modems. So here you have something known as a cable modem termination system, which is, so I'll get to what DSA-LAM is, but it's something like a multiplexer, and it also does a bunch of other things. It does like analog to digital conversion, because once again the internet runs on digital data, of course, modulated digital data, that's how it works. But from this you are only going to get analog signals, so somebody has to interpret it and then send it on the internet, right? And once again, this was meant to be television, so you wouldn't be having like actual digital data that is meant for, you know, HTTP or something like that. You're just having signals, more or less. Yeah. So yeah, and then signals which of course would represent modulated digital data in the end, but they could have any frequency. They could be different frequencies. They could be whatever. Different formats, different modulations. There's so many variables over there. So you would need these modems which convert things in different formats in analog domain, not just in the digital domain. Yeah. So the downstream channel usually uses higher frequencies for this, and you'll see that. Yeah. Okay. This is fine. So the downstream channel uses higher frequency. The upstream uses lower frequencies. That is to say, the downstream speed is higher. Right. The same thing you'll see for DSL as well. But yeah, the worst part about all of this is called shared broadcast. So there's literally like no privacy involved. All the data packets are sent to everything. Like if you send a packet, whatever the response is, everyone will receive that. That's the bad part, because you don't have something like a you know, like in an Ethernet you would have like your own device will have a IP address, right? Like not the IP address, but an IP address that is just for the machine. I think it's called a MAC address or something. Yeah. So you would just have like a machine related address, which the Ethernet ports, which the Ethernet router it uses to figure out where to send the data and what the request came from, all those sort of things. Here, none of that's gonna happen. Whatever data you want, everyone will get it. So this is kind of bad. uh, yeah, and so like if multiple people are downloading a file on a downstream channel, the actual rate will be much lower, because then you have like, okay, sure, all of you are having the same file, and then you just have to do it once. But then again, the network, so this stupid access network, it doesn't actually think of it as being the same file. What would actually happen is like you're thinking, okay, all these people are downloading different files, even though the file is exactly the same. Yeah, so all these requests would be entertained simultaneously. So that's where it's problematic. And so each of these homes will have to filter the data, do some encryption, all that sort of stuff. Okay, and the homes themselves, they'll actually have modems as well, because once again, the data on their television or any sort of internet data, that's going to be digital, but then they have to convert that into analog so that they can transmit it over these wires. Yeah. And what are these fiber nodes? These are the neighborhood level junctions. So it's just like connects through optical fibers, all of this. Once again, there's no splitting, there's no decision making over here. It's like straight up send everything to everyone. And this is called a hybrid fiber coax access network, because you have, of course, it's a hybrid material, right? Some places you have fiber cables, some places you just have copper cables, right? Yeah. Okay, what's CO? I have forgotten what CO was. Okay, that's cable access internet. You have DSL. So DSL works like this, that each home, it's connected to a DSL splitter, right? So for example, over here, the home PC is connected to its own modem, so each home has its own modem. And once again, this home phone should actually also be connected to the DSL modem, whatever. Oh, okay, no, because the home phone is doing the other thing, right? So yeah, a home has like a phone and a PC. So for the phone, there's already a line that is set up. You have a telephone line, right? So telephone lines have this advantage that they don't have to do this analog to digital conversion. It's all analog, right? So you have the central office. So each, like your telecom, basically, it will have the central office, right? So previously just has the telephone network connected to it, and you're just sending analog data everywhere. Now with DSL, what would happen is that the frequency that you were using to send your telephone data, right, your actual audio, it's actually going to be very low, very low, in fact, because guess what, people just don't speak in very high frequencies. So yeah, it's very low, and then you're just going to like, I don't know, sample that or something, or maybe don't sample that, just like send that directly by converting into electricity burst. That's what the telephone network was, right? It's a very efficient system, except you don't want it to just be a telephone network. You actually want it to be connected to the internet. So first, of course, you connect the DSLAM, so that's at the central office. So you connect the central office to the internet, right? So now you also have this all digital data which you can access. But of course, people have to be able to, talk to the internet somehow. So how does that happen? Well, the DSL wires, what they do is they'll use the lower frequencies for the telephone communication, but now they'll also use the slightly higher frequencies for downloading and uploading. So there's downstream and upstream transfer of data. Yeah. So I guess this is the DSL cable, right? So it carries signals in 3 frequencies. So the 0 to 4 kilohertz is just telephone signals, which is the stuff that you talk in, right? The frequencies that you talk in. You have moderate frequency, which is like 4 to 50 kilohertz. This is for upstream. So upstream is still lower. This was the same thing for the cable modem as well. And then you have high frequency, which is 50 kilohertz to 1 megahertz, and that's just downstream. And since the upstream and downstream transmission rates are asymmetric, you would call this an ADSL, right? An asymmetric DSL. So DSL, this wire thing, it's used for little short distances, just connecting to the DSLAM. After that, it's all like about the provider itself. Yeah. So if a residence is way far from a central office, oh yes, that's what a CO was. In that case, he'll have to figure out some other way to connect to the internet. He cannot connect it like this. But right, so what this technology does is actually provide kind of high rates for data transfer, much better than what internet cable was providing. The cable-based internet was providing, right? So what's a DSL splitter? It's basically a passive device which is acting as a low-pass filter. So you have all these frequencies, right? High frequencies like 50 kilohertz to 1 megahertz. There's also going to be noise, which is like gigahertz or 3 megahertz or something like that, right? So those high frequency noise things you have to remove, because if you don't remove that, those will also be there. So even that will be thought of as data. So you have this analog filter stuff going on, and then it combines the signals from the modem, which is this thing. So here what happens is that the home PC wants to send some data packets. They will be modulated using these high frequencies, and then some signals coming from there. And then of course you have this home phone, which is also sending some signal. So it like combines both of them passively. By the way, this is like straight up, like a circuit. It's not an actual device that can do stuff like that's programmable. It's not that. Okay, so it combines the signals by just simple superposition, and it sends it. So this kind of means that your home phone and the modem thing, they're both sending signals at the same time. So at the central office, you either have to do some Fourier transform stuff going on, like you have to do that, separate the frequencies, or these people have an extra restriction that they can only use one at any given time. And I guess the way it happens is that you just do a Fourier transform here, because who would want us of inconvenience? But yeah. So once again, DSL modem is just modulates and demodulates data, right? The digital data, that is to say. Okay, so that's DSL. There's another inferior version of DSL which is called dial-up. So this is also using the what is it called? Telecommunication infrastructure. It's also using that, but it provides much lower transmission rates. So why is that? It has same infrastructure. There's a modem that connects over the phone line to the modem in the internet service provider. Difference is that the modulation is not very good, so it happens very inefficiently in the same frequency range that telephone line uses. So this has that restriction that you can only have the telephone being used, or you can have the internet access. Yeah. So here the central office doesn't have to have the Fourier transform stuff going on. It doesn't have to upgrade anything. It doesn't have to think about higher frequency signals coming to it. But also the person who is using this is like restricted to just being able to send at a particular frequency, right? The same frequency you would actually talk at. So that's a bad thing. Yeah. So it's basically like a very hacky way of accessing the internet without really spending any money at all, and that's why it fails, because even with just like a bit of like money spent in by the internet service provider or the telecom, you would actually have way better internet, right? That's what DSL does. So this is kind of a failure. Yeah. And then you have Ethernet. Before all that, I'll just go through all the other access networks. FTTH is called fiber to the home. So rather than having coaxial cables, you just straight up have fibers. So you have these ONTs, and okay, so I will explain all that. Yeah. So you have direct fiber. So it's just DSL, except that they provide an optical fiber path from the central office directly to the home. Yeah. So active optical network is essentially switched Ethernet. I don't know why I wrote that. Anyway, and then you have the passive optical network. Okay, so that's about the splitter. So the splitter can actually be active or passive. A passive optical network is where the splitter is not going to be doing stuff on its own, right? It just like splits. That's all. Yeah, and this is a passive optical network, by the way. So each home has an optical network terminator which is connected to the optical splitter, so that's an ONT. In turn, the router, the home router, is connected to the ONT, and the residents usually access the internet using the home router, right? So you still have the router that you would usually have, except it's not connected through a modem that you would have previously, because there's nothing to modulate. It's all digital now, and directly connected to an ONT. So ONT receives all the data and then it sends all the data. So this is once again similar to the cable access thing, where all the data is sent to everyone, but yeah, it's much faster. Right, so the filtering happens at the homes themselves, not in the network. So the optical splitter, yeah, it's similar to the fiber node in the cable network. So this is basically the cable network, except better because you have fiber all the way to the home. Yeah, so once again, this requires no power at all, and it does no computation. It just forwards data. That's it. So a bunch of things you don't have to be worrying about, like doing things in the analog domain now, because it's literally like sending quanta of information, right, through light. So it's a better technology. So you can forget all the modulation, demodulation that you'll be doing. Yeah, that already receives cost and like opens up a whole lot of different things that you can do with it, and of course gives higher speed. And then you have the OLT, which is the optical line terminator. So that's this thing. So this is located in the telecom central office, similar to the CMTS that you were having before. So there it was a modem. Here it's just like this thing. It converts between optical and electric signals and connects to the internet via telco. So this is an active thing because it's doing something. It's doing some sort of conversion. So it does the conversion and then it connects to the internet via a telco router. Yeah, so this is faster, of course, and this is, here we're talking about the actual scene rates, by the way. That is after the whole restrictions by the telco and all that stuff. So even after all that, the average downstream repeat for this optical fiber stuff, FTTH, it was 20 megabits per second, while that for DS it was just 5 megabits per second, and for cable TV it's just 13 megabits per second. Yeah, and this is of course like outdated. Now you have very high speed internet, so you would have like 100 megabits per second and 65 megabits per second upstream. Yeah, but then again, now the technology is also slightly better, isn't it? Slightly, well, actually that's a lot better. Do remember that this stuff, these rates that you're seeing, they're mainly because of the telco not allowing full throttle by any of these, right? So there's this whole thing about what is it called? Yeah, I forgot. Yeah, traffic intensity, right? So they want the traffic intensity to be low enough so that like people can, not create too much of traffic, something like that. And also they want some benefit, like they want some money coming out of it. Okay, and then you have these things like satellite links. So these guys, Starband, HughesNet, like these are satellite access providers, and you just directly connect to the satellite, and this is going to give you very, very low speed, except that this can be done without an access network. So no need for a tower, no need for a mobile thing, just do it. And let's go to the mobile thing. Actually, the cellular data, so this is actually very similar to Ethernet. So actually we should go to Ethernet and Wi-Fi first. Yeah, so an Ethernet switch, this is the packet switch that serves not servers. It serves many computers or other Ethernet switches from the same Ethernet coaxial cable. Alright, so this is once again just like switch. It's more or less a passive device. And then you have the institutional router. So this is an active device. What it does is that it connects to all the Ethernet switches or end systems in the local area, and it performs the operation of routing. That is to say, based on your device's IP address, not the IP address, it's more like the MAC address. It figures out who sent the data, where should the data go, all these things. And the router is connected to the institution's ISP. And when we'll get to the IP protocol, we'll probably figure out what this really is, how it does that. But right now, we don't have to worry about it. Now, Ethernet and LAN, these are very, very fast. Of course, the reason being, what was the reason again? Yeah, I kind of forgot the reason. Oh yeah, it's actually a good technology because you have routing and all that going on. Rather than everyone getting everything, giving enormous amount of traffic intensity and all those things. So, by the way, the traffic intensity is like, it makes the speed go down exponentially. So just be aware of that. You want to have the traffic intensity as low as possible, and this can be proved statistically. Yes. Anyway, so the transmission rate reaches sometimes even 1 gigabytes per second. Meanwhile, the institution servers operate on gigabits per second. Yeah, so servers, by the way, when I say servers, I mean like very big devices whose whole purpose is to just send and receive data. So they're supposed to have a larger share of the traffic intensity, and that's why they operate on gigabits per second. Okay, Wi-Fi. So now that you have an Ethernet setup, you can just look at your Wi-Fi access point and realize it's actually connected through wires all the way to your some office, right? So what happens is you don't connect to some random port like you would connect a cell phone to a tower. Instead, whatever Wi-Fi access you see around you, that's what you'll connect to, and it will communicate through radio spectrum. And over there in the, I don't know what to call it, I'm just gonna call it Wi-Fi port. So the Wi-Fi port interprets the radio frequencies that your phone is sending out. It converts it to digital data and then analog data, and then it communicates through the Ethernet. Yeah. Then you have cellular data, which is just Wi-Fi, except you have towers. Like, you don't have just Wi-Fi ports, Wi-Fi access points. You have straight up towers, like very big towers which have very high range. So you can connect even when you're like 10, 20, 30 kilometers away. Yeah. Except you have way slower speed because one, you have many devices connected to the same tower. Towers are very costly setup, so you would ideally want many people connected to the same tower, right? And also it's like there's a lot of like errors that occur because of that distance that you have. So you have to account for all that, which probably takes a lot of time. But that's just a guess, by the way. I'm not sure if that's true, but I'm guessing it might be true. So because of all these factors, you have very low internet speed, right? So on a Ethernet you would reach like 100 megabits per second. On your mobile data, you're not gonna reach that. You'll probably just reach like, I don't know, 20 megabits per second. And so there have been many different variations of the cellular data technology. You of course started with just normal cellular data, then you eventually like went to 2G, 3G. From 3G, there's like you go to LTE, which is like long-term evolution. I don't even know what that does. And then you have like 4G and 5G, right? Yeah, so you can have a theoretical maximum of 20 megabits per second with FG, with 5G, and with 3G it's just 1 megabits per second. So you can literally like go to an internet speed test and see what is the download rate for your cell phone without the Wi-Fi connected, of course, and also see what it's going to be on your laptop with Wi-Fi connected, and you'll see there's a difference. So this is mainly because phones are supposed to be, well, phones and not computers. They aren't supposed to actually download all these high quantities of information, although we make them do it. We abuse them. But they're not supposed to be like that. They're supposed to be cell phones. Okay. Oh yeah, I don't know why I wrote all this. Oh, this was this was, by the way, a response from ChatGPT. Yeah. So Wi-Fi spectrum isn't like licensed, by the way, as in no one owns the spectrum, but cellular data they do own it. There also used to be these things. There are these things known as FM radio, right? So those are like straight up just radio waves being transmitted, like through air, not air, through. Okay, light doesn't have a medium, but you know what I'm trying to say, that it's just radio waves being transmitted without any like wires or anything. So like when you're going on a car, traveling in a car, you can still have a radio, but you can't have like general internet access. Yeah. And so radio bands, frequency bands, those are licensed. Like people own them, right? In a state, a particular radio band, it's owned by some radio, what is it called, company, I don't know. But yeah, like when you go abroad and you will see that, okay, the same bands are like being used by somebody else. That's because radio is more or less restricted to one particular state, right? It doesn't go all the way around the world. Yeah. So that's FM radio, frequency modulated. I wonder if there's amplitude modulated. I don't think there is. The reason we got frequency modulated was because you had very long frequencies which you want to be converted to high frequencies, otherwise they would be like not able to reach everyone. But yeah, whatever. Okay, now we can actually go to what an access network is. So far we have really been seeing access networks everywhere, but formally it's basically the local network used by a group of end systems to access the internet. So it's at the edge of the internet. Yeah. And the parts involved in the internet itself is what we call the network core. That is all the routers, all the communication links inside of the network itself. Yeah, internet, right? So the data that leaves the ISP central office, it goes into the internet, the network core. Till that point, it's mostly just the access network which we are talking about. So for example, an Ethernet switch and a DSLAM, these are link layer switches. A DSLAM is basically a very big multiplexer, right? It's the DSL AM. Why is it called AM? I guess I should go back to DSLM. Yeah, what's a DSLM? Yeah, access multiplexer, right? Because it's access network. Yeah. So over here, you do have some sort of decision making, and that's mainly done by this DSLM thing. Okay, so that's this link layer switch, Ethernet, DSLM, and you have non-examples. So some things that are not link layer switches. That's the FTTH optical splitter. So okay, I thought that was a switch, but okay, that's not a switch. So a link layer switch forwards the packets between devices on the same access network using MAC address and not the IP address, and it doesn't just forward it. So this probably is not a switch, and it's just like, I don't know, some sort of passive device. I was thinking what it was, but okay, whatever. And then you have the physical media, which I don't really want to talk about, but okay, you have guided media where the electricity or whatever signal there is, it actually flows through the like structure that you have set up. Unguided media where everything is everywhere, that's Wi-Fi, satellite link, cellular data, it all basically is just radio frequency. Okay, and then you have the propagation time and transmission rate, IME transmission rate. Okay, I don't know why it's IME. Oh yeah, okay, this is actually I think an important thing. So the actual transmission rate isn't dependent on the length of the wires or how big the wire is or anything like that. Because if you're going to be sending a very big stream of packets, what will actually matter is the time. So the gap between two packets. That's all that really matters. Like it's basically the transmission rate isn't dependent on the actual speed of the thing on the physical medium. It's dependent on how close you can keep two packets or two bits on that medium, right? It's that. Yeah. And so it's more of a technological issue rather than a physics issue. Cool. Okay, so that's the network edge. Go to the network core. So you have a store and forward packet switching. So what routers usually do is that they store all the information that they have and then they send it to like based on whatever route you're going to have it, they send it to something else, right? And usually there's no delay between the packets. So route must basically like queue the packets and then it sends. So this delay for queuing is called the queue delay, right? Yeah. Sometimes when the buffer for so of course you have to store it somewhere, right? So that's the output buffer. That is to say the buffer for everything that is supposed to be output eventually. So there's one output buffer for each link, by the way, each input link. Even then, when the sorry, so when the total capacity for all the like output buffers combined, it's overflowing, you would obviously have packet losses. Yeah. So there are many different ways that this could happen. In like circuits, you don't have this happening, but in packet switching you do. Okay, this is like all the way to the IP protocol. We don't want to go into it. Yeah, so this is what I was talking about, circuit links. When you don't want this to happen, when you don't want the packets to actually wait in a queue, you would have what's called a circuit link. That is the path that the packets are going to take, that's already pre-computed and then it's always open. So it's basically like a flow-based system at that point, that everything's going in and there's no waiting or anything, everything's just going out as well. So each packet waits, but the whole signal, it may not wait, right? If there's just one signal, it does not really wait. Like the router just has to get all that information, and as it's getting it, it's also transmitting. So it's basically just whatever is the output transmission rate, that's the new speed of the signal. It's as if there was no waiting at all. So packets wait, but the stream does not. That's kind of important. But then again, if you have like very less amount of information, so you can just think of like just one packet from each person being sent, then you have to worry about the delay that the packet is going to have, like say in a multiplayer game or something like that, but you can't keep the TCP connection open. You can't have this congestion control thing already going on. You have to worry that yeah, that like what's the traffic intensity, how fast can I send stuff, what's the delay, all these things. Okay, there are different ways that you can break an access link, a link, it's just called a link, I think, communication link, into multiple slots, so as to say. So one obvious way is just time division. So you just like literally break things into slots based on time. It's like a round robin approach, where each slot you'll have one of the input links, so in a router of course, input link sending out data. The second slot will have the second input link sending out data, and so on. So that's time division. And then you have a slightly superior thing which is called frequency division. So this is used not as a protocol to like figure out how to, in what order to do stuff. It's just like a better technology, right? So like frequency modulation and all these things. Yeah, that's basically what I was talking about. Radio, right? FM, that's what FDM is. You're breaking the medium, which is basically radio spectrum, into different slots, and each slot is being assigned to different sender. Oh yeah, and this is like complete bullshit. This picture is like just an analogy. You don't actually have a real like physical circuit. Yeah. So packet switching is just more efficient for the full network because you don't have to do this pre-allocation stuff. Well, circuit switching is more reliable for a particular person, and so there are people who support different things, and yeah, I mean for different purposes you would use different things. Like for HTTP, nobody is going to use circuit switching because who wants a reliable transfer rate for an image? All you want is that the image should get loaded as fast as possible. So that's going to be through packet switching. Oh yeah, and this is the whole internet in like a bird's eye view. So you have these access networks, so for all the internet service providers which are like local, they are connecting to the regional internet service providers, and these regional service providers are connecting to tier 1 service providers. So tier 1 providers are those which do not pay to anyone, right? So the access internet, so access ISP, they'll have to pay to the regional ISP to access their like network, but then the regional ISP has to pay to the tier 1 ISP to access their network, but tier 1 does not pay to anyone. They can access everyone else's network. And when I say network, what I really mean is all the different devices this ISP has peered with. So if let's say you have two regional ISPs and they have all these access ISPs connected to them, if they peer, then this regional ISP also has access to all of these guys without having to go through the tier 1 ISP. So it's beneficial for it, right? Usually this thing is for comparable sized networks. This thing is done without any settlement. So it's just like they decide, okay, you are a good person, you have enough assets, this guy has enough assets, so let's just, like, to put it frankly, get married or something like that. But basically this has now access to all of this, and this has access to all of that, and this happens very organically. Like, this is people making decisions. So yeah. And then of course tier 1 ISPs don't really pay to anyone else. Two tier 1 ISPs can in fact peer, but there's not going to be like any sort of settlement going on, like any money being transferred. And then you have these guys, content providers. For example, Google is a big content provider. What it does is that it peers directly with the regional ISPs, it tries to not peer with tier 1 ISPs or all that, and it only does that for the particular services that it's providing, such as YouTube or Google search. So it's not going to provide full internet access, as in you can't really like upload stuff to Google's data hubs, right? You can't, it's just not going to happen. Instead you will have to use some other way. When you use Gmail, you're not really uploading stuff. When you use Google Drive, you are uploading, but that's a completely different service than YouTube. If you're just going to use YouTube, for example, you don't upload stuff like that. Of course you can do the YouTube create thing, but that's a different thing. That's not the streaming service that you're talking about. The YouTube streaming service, it does not do general internet access. From YouTube you can't search some random like internet link, right? You'll only get things which are in the domain for YouTube. That's what a content provider does, that it does not care about general internet access. Yeah, and it directly peers with the regional ISPs, or at least tries to avoid tier 1 ISPs or even these access networks, in fact. So that way it can get the data directly to the access ISPs, and it does not have to pay that much to do that. If you're not gonna be like providing full internet access, you don't have to peer with a tier 1 ISP or something like that. So if like Google wants to provide YouTube as a service to a city, let's say Mumbai, what it would do is find regional ISPs for Mumbai, and it would peer with that. It would set up a data center in Mumbai, and it would like directly give uh, yeah that data service IP address will be there for the ISP, right? It's in its DNS directory and all that. So it forgoes all the connections to the other things, right? The like Google's data center is not going to access the internet through the regional ISP. That's not what it's actually doing. It also does not have a network of people connected. It just has a network of data centers connected to the people. So it does not operate similar to what these service providers are doing. Right. And then you have these things, internet exchange points. These are like literally buildings, very big buildings where a lot of service providers basically like connect to each other. Yeah. Okay, what's POP? This is the point of presence for a service provider. So like wherever the regional ISP has its offices, people can connect directly to that, right? So that's where the access ISPs will connect, and similarly like the people themselves will connect to the access ISPs where their central offices are. Yep. So anyone who doesn't have to pay for the service for their network being connected to somebody else's network, that's a tier 1. Yeah, so this is another thing which people do. For example, this ISP that you see over here, it's connected through this regional ISP, sure, but it's also connected to tier 1 ISP, and this regional ISP is actually also connected to tier 1, and of course a bunch of other like things. So why is it doing that? If it already has a tier 1 connection which is already connected to everyone, why does it have to connect to the regional ISP? The reason is that if the tier 1's infrastructure is somehow off, like for a day their centers are off, in that case it's still like people over here who are connected through the access ISP, they would still want to connect to like other people, right? So this gives this access ISP some sort of reliability that okay, through this access ISP you can actually connect at any given moment. Even if the tier 1 ISP is down, you can still connect to the regional ISP to something, right? And this regional ISP is connected to some other tier 1 ISP, so you can in a sense connect to everything, even if this guy dies or something like that. Yeah, that's multi-homing. So this access ISP is like a home for both the tier 1 ISP and the regional ISP, and of course the other tier 1 ISPs. You get the thing. Content providers, yeah, these are all the reasons why content providers do what they do. So of course it's low cost for Google. Of course setting up the data center is costly, but once that happens it's very low cost. And also there's security, because you are not going to access the full internet, right? People are not going to access that, and also the control over that network. So instead of like having a site, you actually have a data center. Okay, so that's chapter 1 more or less. And then you have these guys: delay, loss, throughput, packet switch networks, which so far I don't think these are going to be all that important for what he's teaching right now, but yeah, these are going to be important when I'll finally like start to solve questions. But yeah, there's like a bunch of delays. There's transmission delay, there's propagation delay, queue delay, processing delay, and then there's some other phenomena that's happening like packet loss, end system packetization delay, end-to-end delay. End-to-end this is like all of these delays combined. But yeah, so I'm just gonna run over these things very quickly. What's the transmission delay? The transmission delay is the time taken to actually transmit. So like for what was I going to say? Yeah, so it's a time taken for the packets to actually be transmitted, right? So it's like the packets will be having a bit of a space in time um, between them. That's the transmission delay. Yeah, okay, this is not very accurate. It's not just going to be L by R, it's going to be more than that, because you would actually place the packet slightly farther away from each other than just like contact, but fine. Oh yeah, okay, so suppose the packets had no delay between them. Then the transmission delay equal to the full stream of packets due to a single store and forward type of like packet switching. It's L by R. Wait. Yeah. Okay, this is slightly related to queuing delay, I think. I mean, there's a bit of a, I don't know, like mixing of concepts there. So okay, the propagation delay is probably the easiest thing. So when you send a packet, it has to reach the other end of the communication link, right? The time it takes to reach there is basically the propagation delay. And in an ideal setting, the time would be 0, but it's not. So it's just the distance that you have to travel upon the speed of the thing, right? The speed of the information in the medium. That's all. That's propagation delay. And then you have queuing delay. This is kind of an interesting. So for each packet, you have a queuing delay. Yeah, just to say, like all the other packets that are already there, you have to actually wait till they are processed. So that's the amount of delay that you would have. Yeah, so usually you would think, okay, there's no queuing delay, because if the transmission rate is the same everywhere, in that case, whatever rate the packets are being sent are also the rate that, so whatever rate the packet are being sent into the router are also the rate at which packets are being sent out. So there's no queue that is actually going to form, right? But this isn't just about one link. If it's just one link, one input link, one output link, this is doable. If there's multiple links, right? There's 2 links that are going inside. In that case, you do have to have queuing delay. So suppose n packets arrive simultaneously, so there are like n links, and each link sends a packet. In that case, the ith packet has to be transmitted, I don't know, so like ith in order of transmission after I minus 1 times L by R time, right? So it's the transmission delay of all the packets sent before it added up. Yeah. Yeah, this seems right, I guess. Huh. Okay, let's go to packet loss. Oh, that's a processing delay, right? So the last source of delay is the delay due to the processing done by the router to decide the output. You need the packet loss, which I'm not interested in. But basically, it's like when the buffer overflows, the output buffer, you start to lose packets. That's an unavoidable situation. And that's why you have to keep traffic intensity low. Sometimes the end system themselves will possibly delay the transmission of the packet. For example, when the end system is sharing the medium with other end systems. I don't even understand what this actually is, but that was written in the book, so I just have that there. It's probably like for some sort of synchronization. Yeah. Okay, packetization, voice over IP. Oh, okay, so instead of just having a telecom, it's a telephone network, you just have HTTP based voice calls. So the sender end system must first fill the packets with encoded digitized speech before starting transmission. This can cause a delay. I get it. Yeah, sure. Because the signal reaching is just not enough. You actually have to have the whole signal, a packet of the signal processed, right, converted. Okay, the formulae over here are just like completely trash because they're making a bunch of simplifications. But let's say suppose there are n links between the source and n minus 1 routers. The delay they're saying is n times the processing delay and propagation delay, n minus 1 times the transmission delay and the queuing delay. Yeah. So okay, the routers, I get that you would have a queuing delay, and you would also obviously have transmission delay because it has to be stored and then transmitted. So it's not like you get the bit, you just transmit it. You actually get the bit, you store it, and when the last bit comes there, that's when you start transmitting. So that's when the first bit is transmitted. So that's why you have transmission delay for each router. Yeah. So I get that for routers you have transmission delay and the queuing delay. It adds up for each router, in fact. And we're just talking about one packet over here, by the way. But then for the process, so for the end host themselves, you also have processing delays, which is true. You still have to decide where to send and all that. So you, I guess, do have processing delays. Yeah. And then you have the propagation delay. So that's because of the n links. That's completely fine. Right. So in the book, it's oversimplified because we are saying that T transmission is also there for the for what? For the end systems themselves, and that the queuing delay is 0 everywhere. So that gives us this thing. Yeah. Right, so that's what the trace route does. It's very similar to what DNS does, but you know, unnecessary. That's all. Yep. So it's just basically the bottleneck. That's what you have to worry about. That is what the throughput is concerned with. It's not concerned with the delays at all. It's concerned with when you're sending a stream of packets, a very, very large stream of packets, then what's the rate at which packets are going to reach. And that's basically just the bottleneck. That's what we're going to be concerned with. We're not going to be concerned with the delays that happen for the first packet or the last packet. Service models, I don't know why it's called service models. Anyway, so you have all these different layers. In the OSI you have two more layers, that is to say presentation layer and session layer. But yeah, and all of these have this encapsulation thing going on. So yeah, like, you know, your I don't know, your packet for a particular layer, right, the service data unit, it encapsulates all the information of the previous layers. That's what encapsulation means over here. Okay, now I do understand why it's called encapsulation. Previously I just didn't understand. I thought, okay, it's just some stupid word that they're coming up with. Okay, and then you have this thing. This is a kind of an interesting section. Networks under attack. Yeah. Okay, so one thing, that's botnet. It's kind of a very common terminology. So the network of the end systems that are all affected by the malware is called a bot. It may not be a malware, by the way. It may literally be like a person controlling them. And you have viruses, which aren't like people controlling it. It's just like straight up, you know. Yeah, right. But yeah, okay, what do viruses do? They require some interaction to infect, whereas worms, they don't. Worms do not require any interaction, and these enter just because of some vulnerable application that you have, right? So that's why, like, you have to update your operating system every once in a while. That's because of these burns. Okay, now let's study some classic attacks. You have the denial of service attack for a network. So what usually happens is, if the like what the person wants is that people should be able to access the network, right? Like, let's say you have a HTTP server which you don't want people to access. What you would do is you would send thousands and thousands of packets with the destination IP address of that server, so that it's like overwhelmed, and then it cannot actually answer queries that, like, genuine queries that the people have. But this is actually easy to figure out, because what would usually happen is that inside of the network you'd have a flow, a circuit which is extremely high. There's it's 1,000 times higher than every other flow that you have. Yeah, so it's still easy to do that. What isn't easy to figure out is a distributed disruption of service attack. Now, this is something that people do for DNS, or that was once done for DNS, and yet it didn't actually like do any shit to DNS. But yeah, this is a bandwidth flooding attack. So the upstream router will be able to figure out that the traffic from the so this is okay. Normally for a DOS, the upstream router will figure out like the traffic from the attacker host is large, will block all the traffic from that source. To avoid this, what the attacker might do is that it will actually have a bunch of slave computers, slave devices in the network, and they'll all send packets, like let's just say one packet every slave, to the router or to the server, right? And yeah, so this thing is probably the victim. And this guy now cannot actually answer queries for genuine queries. Yep. And so I don't know why people do this disruption of service, because they're literally using the service and just not using the service. So what do they even get out of it? I don't know. It's probably like they blackmail the company itself, that if you don't, give us some money, we won't like stop this, or some stupid shit like that. I don't know. Frankly, I don't know why people do this. Oh yeah, okay. There's also these kind of attacks. There's obviously bandwidth flooding, which we just saw, which is actually very like a genuine concern. Then you have these other two. So one is connection flooding, where just like have thousands of connections being built to the same host, which floods the host, and then the host cannot actually have any genuine connections, which is similar to bandwidth flooding. Except with bandwidth flooding, you're sending packets. Here you're just connecting, right? Just connecting, just having a TCP connection open. And that's the issue with the protocol itself. It's not the issue with the network infrastructure. Bandwidth flooding, it's an issue with the network infrastructure. What's a vulnerability attack? That's like an issue with the operating system itself. If you have a vulnerable operating system, what a person could do is send handcrafted messages, application layer messages, to you, and then your OS would just pick it up without even knowing, and then whatever service you are using, you just stop. Now, this is all cool. This is like disruption of service, but it isn't as cool as packet sniffing. Packet sniffing is basically when you have a shared medium, you extract all the packets sent or received in that medium. So let's say Wi-Fi, and we're probably going to do this in this course that I'm taking. So just so you know, I'm doing some cool stuff. Okay, so you're going to process this with some heavy computation. You like decrypt it or whatever, I don't know, and then you extract sensitive information from it, and you basically do some illegal activities with it, like, I don't know, drain somebody's bank account. Yeah, and even if you don't do this, even if you don't actually decrypt and do all that, you can still figure out at what times does some person use the internet or something like that. So that's still enough information for you to do phishing attacks, which isn't a good thing, because yeah. And packet sniffing is so notoriously hard to find, because packet sniffers are usually passive devices. So the packet sniffer only like detects the packet but doesn't send any packets. This makes it impossible to detect a packet sniffer, right? You could be having a packet sniffer right beside you, probably connected to Wi-Fi anyway. So it's gonna be hard. Your life's gonna be hard for you have packet sniffer somewhere around you. The best defense against this is of course cryptography, because you can't really detect the packet sniffer itself, so all you can do is prevent from sensitive information leaking out. Yeah. And then you have IP spoofing. So this, I mean, once I knew about this thing, I don't even think like spear phishing is anything sensible. Because if you can just do IP spoofing, that is, you can pretend you are a particular person sending packets because you know their IP address or their MAC address. You can make that person's life hell. You can send weird email messages and all that sort of stuff, right? Like, yeah, it's going to be pretty messed up. So you can create packets with arbitrary source addresses and contents and transmit these handcrafted packets onto the internet. So impersonation, done, easy. There's no need for actual spear phishing. Just do this, right? And so this is solved using endpoint authentication, which I don't really know what it is yet, but if I had to guess, it's something like SSH or something like that, like keys, even more cryptography. But anyway, that's chapter 1. Now you're chapter 2. That's part. So it's gonna deal with actual application layer protocols. The first protocol that everyone should know is HTTP. So HTTP messages are like these. You will have a method which is usually a get. So I'm talking about request messages. You'll have a get, post, delete, update method. Those are the different things that it can have. Yeah. So that's you have head input. I don't think it's an update. There's no update. Update is for SMTP. Get is pretty easy. You just like get a bunch of files. So I'm going to call it file for now, but the technical term is called object. Yeah. So file is specified by the URL for the file. It's like an abstract address of that inside the server, right? So just think of how you would have a file described in a folder. It's kind of similar to that, right? And the server itself is described by its IP address, and the process on that, which is actually going to just the thing that you're actually going to communicate with, it's described by the port, right? So you must have been familiar with this thing: ports, domains, URLs, right? Host names. So yeah, it's just all that. You have a method, then you have a URL, which is like the file that you want, the version that you're using, the HTTP version that you're using. So you'll have probably something like HTTP 1.1 or something like that. And then so CR is a carriage return, LF is a line field, and you have a header field name. So HTTP has a bunch of headers. For example, there's a conditional get, which has a very long name for a header, which is basically like telling it it's used for cache. But yeah, right. But yeah, these are all the methods. You can do a simple get, which just fetches the object. Yeah, you can use a delete, which deletes an object. Put, which is used to upload the object. And post, so it still fetches the object, but it actually uses this body. So in a request, you would also have this body, right? So usually in get request, you don't really care about this body, it's like empty. But in a post, you would use the input fields in the form. So this is somewhere in the body to actually tell the server what to return. So you can send slightly complicated messages to the server. Yeah. You can also do this in a get as well. There's this question mark delimiter that you can put for a URL, and then it will interpret that. It will do that, all that. But yeah, why have that sort of thing? You can just have a post message, because you know the URL itself is going to be there somewhere, and it's not encrypted. It might be clear text. Okay, we also have the head. So it's similar to get, except it doesn't actually return the body. So you might think, okay, what's the point of doing that? It's used for debugging. It's used for like developers. It's not supposed to be used by actual like browsers. Then you have yeah, that's all the methods. Okay, so the URL is just the path of the object on the server. Okay, I'm saying path, but it might be slightly more abstract than that. It might just be any like URL being matched to some actual file location. Then you have version, so this is HTTP version, and your header fields. For example, some header fields are connections. You can have a connection close. What it tells is that once this whole thing is done, close the TCP connection. You could have a host, which is basically like a redundant or like metadata sort of thing, where you're telling what's my host name, yeah, or what's your host name, or what's the destination host. Oh yeah, okay, in this case it's a destination host. In SMTP also you have to tell your host name, but okay. So in particular this is the destination host. Another popular field is the connection, so it specifies whether to close the connection to open. Two other headers are user agent. This is the browser type that is making the request, and the accept language. So this is like, so at TI I was like continuously questioning why you have Chinese and Japanese translations for your website, but now I understand, okay, that is actually important. Like, yeah, it's so important that you even have a whole, like, I don't know, a header field in HTTP itself, so it's accept language. So based on different languages, if there already is a language, right, it exists on the server, you would have different versions of the same web page returned. It might seem stupid to you. It might seem like, okay, why do that when you can just have that in the URL? But trust me, people do this. This is an important thing in industry somehow. But yeah, you're right. You also have this user agent. That's the browser type that is making the request. Right, French, all that. And then you have the entity body. So this is empty for the get. For post, it's filled with the name value things, right? Whatever form fields that you're going to have. And then for the response, you don't actually have all of this. You have a slightly different format, but the entity body is basically the entity that you got, the data format. So let's just look at the response message. So of course, every kind of message application there, it has a status, it has some explanation of the status, right, what exactly happened, if it's an error or something, and if there's everything going right, then it has the body. So yeah, so you have the status code, you have the phrase for the status code, you have the version of the HTTP that you're using, and then you have the entity body, and of course you have the header fields. The entity body only starts after a blank line, so you'll usually have these sort of delimiters. For HTTP it's a blank line, for SMTP it's a dot. You have these things. So it's the same thing as in the request. Status code 200 okay, so everything went correctly, 301 moved permanently, your requested object is not there, and its new location is going to be the location header. And then you have the 400 bad requests, this is some generic error, and you'll have the phrase describe what exactly happened. Okay, now some like modifications to all this. First, let's go to a web page. Actually, you know what, web page is kind of complicated. Let's just go to cookies first. So a cookie is basically when the server itself is storing some information about the user. So usually that doesn't happen. Like if it's just a static page or something like that, it won't happen. But if you are using something which has some actual backend, right, like a real site, like when you do a Google sign-in or something like that, what will happen, or even if that does not happen, right, even if you don't actually do a password and all that sort of stuff, you still have these cookies which track users, which like figure out different attributes about you. It like stores it in the database so that whenever you come back, it will know more about you and then it can serve you better. That's just what a website does. So what it actually does is, like, inside of your like browse, so in your browser application, you'll actually have a cookie file which stores all these mappings. So it's like for different host names, you'll have a number, and that's the cookie. So the way this number appears there is if you're going to get a set cookie header in the response. Yeah, so you just have some usual HTTP request, and then this website, it decides, okay, this guy is unknown, let's ask him to set a cookie. So they ask you to set a cookie, you do that, and the next time your browser wants to communicate with this website, it will use this cookie, so that whatever data was stored in their database, they can use it and they can serve you better, right? So yeah, yep, that's what it is. So this is called cookie file that you have, right? So set cookie is a header which comes in the response messages. That's that. And then you have you also have all these different ways that you can send HTTP. You can use HTTP. We'll get into how HTTP exactly works, but for now, just like how to use HTTP is kind of more important. Yeah, and then you have this web cache or proxy server thing. So what a web cache does is that it gets all these requests, HTTP requests, and on behalf of the client, it will request the actual server, and then it will get something back, and then it goes there, right? So it's like an intermediate server. So this won't happen for a normal direct HTTP connection, but if you're using, I don't know, some industry proxy or like some university proxy, you would actually have this. Like the request would actually go through this machine, and then it will figure out whether or not to send the request, what exactly to do, all that. And then it will actually communicate to this request response thing, and then send back the response. So for example, like on ITGN, you have like some websites which are blocked off, right? There are usually like some gambling websites which are blocked off. How do I know? Don't ask me. I don't do gambling. Yeah. So okay, let's think of a better example. At Texas Instruments, where I was working, you have some sites which are blocked off, like let's say Perplexity. You can't access it. You can't access Perplexity because they have some restrictions that, okay, people will send data to Perplexity and then we might lose some critical data. So they have a proxy set in where you just aren't allowed to access some websites. And that's what a proxy server does. And you might think, okay, this is just some sort of chain that you have on the employees. But no, it actually has a more important use, and that is serving as a cache. Yeah, so not only does this like communicate for you, it also actually stores whatever you communicated, so that next time you want that, you can just get it directly. You don't even have to go to the origin server. So for example, here you have a local network, an institutional network, and these are all connected to some common router or something, and then you have a 15 megabits per second access link to some ISP, and the ISP is connected to the public internet, right? So your institute is connected to some ISP, the ISP is connected to the public internet, and the issue with this setup is that your institute network, it's going to have a lot of traffic. So this for 15 megabits per second access link, it was good enough and there wasn't a lot of traffic, but now with the 100 megabits per second LAN and very hi-fi local network that you have, and lots of people want to use this thing is going to have a traffic intensity which is very close to 1, which is an issue, because if it's close to 1, it won't work. It will basically just not work. People wouldn't want to use it at that point. So what the sensible person would do is, of course, improve this, like make it go from 15 megabits per second to some 100 megabits per second, right? What an even more sensible person would do is that, why even do all that? Just have a cache, so that the actual number of requests that go to the access network, to the ISP, will be less, right? And I told you, right, it's exponential, like the time that you would have to get some data from the internet is exponentially related, negative exponentially related to the traffic intensity. So getting traffic intensity down from even 0.8 to 0.6 can mean a massive difference. And that's what a web proxy does. It not only acts as a, some sort of chain on you, it also acts as a cache. How will you pronounce that? And that's important because not only does it actually like make it better for you, because now you have like more hits. So whenever you have a hit, it's already there, so it will just get that to you. And then in case of a miss, it doesn't have to, so it just like goes all the way to the internet, it gets that, and then it stores it, so the next time you want it, you just get that. So it's the usual stuff that you have in architecture. There's that, sure. And even if you don't consider the traffic intensity going down, it would still be advantageous to have a cache, right? It's a good thing. Except you also have the major thing that it does is not just that it acts as a cache, it also acts as a traffic intensity reduction, and that in itself is going to give you massive speed, because you'll actually have less requests going over these access links. And you might not like appreciate it right now, but when you actually do the calculation, and look at the numbers, you'll realize what this thing really does. One of the best examples of this thing is the DNS servers. Inside of DNS, you also have a cache. We'll get to what DNS is, but there it's a really important thing, because the root servers, you never want to actually access that. There's only like 400 root servers, root DNS servers all over the world. So you can just imagine the amount of traffic that they'll have. So normally you just don't want to go to that point, but that's the first point that you have to go. In fact, in the normal naive DNS usage. So that's why you really need cache to bypass these servers. Yeah, that's a web proxy. And yes, there are a bunch of calculations that are involved, but then they just make up numbers, so I don't want to do that. Then you have the internet delay. So inside of cache, so inside of this infrastructure, sorry, not this infrastructure, so once the data packet leaves this place, right, the office for this institutional network, and actually goes to the internet service provider, it has to actually go to the internet, right? And from the internet, some data has to come back. So that whole thing is what's called the internet delay. Right. So, okay, sorry. Once it leaves this ISP, yeah, then it's the internet delay. This is still just the access link thing, which is called the delay. But yeah, that's called the internet delay. Yeah, which is sometimes huge, mainly because of the figuring out of IP address and all that stuff. Okay, next thing which you're going to get is conditional get, because when you have a cache, you also have to have a way to update the cache, right? So say some person does a get request, and it goes to the proxy also caches the thing back, so like it does the whole process. It like sends on its behalf that thing, it forwards it gets some response back. This is maybe the response that it gets back. It will put that in the cache. Yeah. Also, so notice that there's this header that is called last modified. What this is saying is that the file that you wanted is last modified on Wednesday, 9th of September, right? So this proxy thing, it will store that. It will also store this last modified thing in a database. Yeah. Now the next time somebody does a get, it will, instead of like getting this whole data, it will just contact the other end system from where you want to get the file, right? The server, the HTTP, you just have servers, and it will see if the last modified is still the same. If it's not, it will have to get the data, right? Yeah. So the web case first verifies if the object is latest. So it sends the get message to the server, and the server responds with this. So it's still just 9 September, so that it's not updated. If it's not updated, and then you don't have to get the file. So just send back the file that is already cached in your system, right? So the object was not modified, server responds with this response. Oh yeah, okay, there's also this extra header that you have to notice. So it's an if modified since. So in the case that the file is modified, send me the file. If it's not modified, don't send me the file. It's like that. So instead of doing a instead of like requesting it to the server 2 times, where one time you just check if it's there and the second time you check, you actually get the thing. You're just doing it once using this if sort of statement. Yeah. So it's similar to head, like it's like combination of head and get. So you could just be sending a head message first, that okay, just tell me the metadata about this file. I get that, and I figure out okay, this file is actually outdated, I need to get the actual file, and then you do a actual get message, and then you get the file, you once again store it in your database, and then you send that to the client. That's one thing which does it 2 times, and then you can just do it 1 time if you just do the if modified since, right? So it like reduces the time by half, and it's also cleaner because it's also cleaner. That's one thing. So you might think, okay, but in the end you are still communicating with the internet, so isn't that defeating the whole purpose of having a cache? No, it's mainly the transmission rate that we are actually worried about. We're not all that much worried about the delay. We're worried about having a lot of data flowing through the 15 megabits per second access link. What our main aim is to reduce the traffic intensity on that link. That's it. Once we do that, the cache can do whatever it wants, and that's why we're doing this. This is what the cache does. That it doesn't really care about the delays. It cares about the throughput, and it cares about the intensity. Yeah. But that also kind of makes the calculations which we did for this section completely stupid. But I mean, it's okay, I guess. Yeah, I guess. Okay, what was the calculation that I did for this? Oh yeah, it's a response time. Right, it's just basically dependent on the traffic intensity. That's it. You don't even worry about that 1 megabits per second, 1 megabit file that you are sending or receiving. Just care about that. And so this thing is kind of flawed, I guess. Well, we'll do some questions and then we'll figure out how flawed it is. Okay, that's mainly HTTP. Then you're going to go to electronic mail, that is SMTP. Oh, I didn't actually tell you what HTTP does, did I? No. Okay. So let's read through all that. So let's start with very basics. Application architecture. So network architecture, it describes how the computers are interconnected, but the application architecture describes not that. It actually describes for the network application, in what ways do the the computers actually interact. It's not just how they're connected, but how they interact with each other. So like things like servers or mail servers or these things, these are not dependent on how they're connected to different devices. They're dependent on how they interact with other devices. So you might have a client server architecture where you have a bunch of servers, and the clients communicate with the servers directly. They do not communicate with each other. Yeah. Or we could have a P2P architecture where the person is connected to the other person directly. They might have a hybrid architecture, like what WhatsApp does, or what BitTorrent does. Nothing is truly P2P, by the way. Maybe Bluetooth is, I don't know. That's not even a proper internet thing. Okay, so communication, it happens between processes, not between computers, just so you know, right? It's not like your computer is sending a bunch of data. It's actually like a particular function call is happening in a particular program, which is using your computer's hardware to send out data. That's what it's really like, right? Your computer is probably connected to some LAN wire, and through the internet it's going to send out impulses, and this thing that triggers this is some process running on a computer, not a computer itself. So what you would actually want is communication between processes, and the way this happens is using ports. So you'll have multiple different ports on a computer. Each of them is dedicated to some particular process at any given instance. Yeah. Oh yeah. Also, you have this extra terminology about a client process and a server process. So this is not dependent on the application architecture at all. This is just like the data transfer is like happening like this because the client is going to initiate the TCP connection. That's it. That's what we call a client. Yeah, is the first person to reach out. It's not about how the application actually operates. I mean, it is, but not very directly. Okay, what's a socket? Socket is an interface between the process and the underlying stuff. Just calling it stuff because there's a lot actually that's going on. But yeah, so it's an application programming interface, which you can guess it's actually in the application layer. What's a port? A port is, well, how do I even explain this? Yeah, so like, have you ever used Docker container or connected to some database which requires you to specify the port or something like that? You must have used something like I don't know, Flask or Django, right? You have these ports where processes run, don't you? So it's like a number being assigned. So what computer will do is like it will assign different processes to different ports, and then whatever data is sent out by application, it will say, okay, this port is sending out this information, not like what process is sending out the information, but just what this port is sending out. And then based on the port, the receiving host, it will figure out what sort of application it is or what sort of protocol we are using. So if you are having a web server, it's going to run on port 80. That is to say, it will send messages which are going to follow HTTP protocol. If it's a mail server, it's going to run on port 25, so it's going to follow SMTP protocol, and you have all these things. Yeah, and of course you have these other weird things like development servers running on different ports, Docker containers running on many different ports. But yeah. Then the transport layer services available. So just I know it's supposed to be top down. I don't know why they're talking about it right now, but okay, let's just go through it. But okay, so there's just the services that are available for the transport layer. Those are reliable data transfer, throughput guarantees, timing guarantees. So the throughput is independent of the delays. Timing is not. Timing is basically delays. So in I don't know, a multiplayer game, you might worry about timing. In a file transfer application, you won't really worry about timing. You worry about the throughput. Security. So if you're doing something like SSH or something critical like bank transactions, you would worry a lot about security. And then there's reliable data transfer. So like SMTP uses this. It relies on TCP's reliable data transfer. That was really bad, because it just wants, because it has a very permanent sort of messaging structure, where once you send a message, it's sent. You can't change it. You can't send more messages to update it. It's just sent. So it has to have this reliable data transfer where all the parts of the mail is sent. Okay. SSL, so TCP is good, but it does not have a lot of security things going on. So if you enhance TCP, there's an application layer protocol which we call as SSL. So it's called secure socket layer. Yeah. So TCP or UDP, they don't provide encryption really. They're transport level protocols. The encryption usually happens at the presentation and session layers, mostly the presentation. So what you really need is a layer on top of this, which handles all of this. So that's where SSL comes in. And you must have heard about this at some point, right? If you're like ever worked with web applications or built web applications, you must have heard about SSL keys or these sort of things. That's because SSL deals a lot with encryption. Yeah, so it will take the clear text that is supposed to be sent to the TCP, it will encrypt it, and then it will pass it to the TCP. So it is using the TCP, it's just like building on top of that. So something like an application layer thing, except it's not really application, because it's not an application, it's not a protocol for doing an actual thing. It's a enhancement on TCP using the TCP, if that's making any sense at all. Okay, and this is about what I was talking about earlier, objects and files and all that. So a web page is, you must know, if you have ever built any sort of web application, is basically made of the HTML page that you have, and HTML page is in fact what you have, the images, the different types of data that you have. You could have like straight up SQL databases, I don't even know, but yeah, you have all of that. You have the HTML page, you have a file, maybe an FPG file or something, and you have data in a database. So all these things, they are called as objects. So like in a .db file, SQL.db file, you would have some table. That table is an object. If you want to send that to the client, when the client loads a web page, you'll have to think of it as an object and then assign an URL to it. And that's what, you know, web applications do, that for the URL, it will, the backend will figure out what exactly to send back, and it will send that back. Yeah. But really what HTTP does is that it only takes one object at a time. So whatever URL you type in, whatever object is associated with that, it will just take that. It won't take any other object. An object has to be serialized before it's sent. Like you can't just send a bunch of files at the same time. You'll have to combine the files into some single entity which like encapsulates all the information. So yeah, that's just the structure of that page and how HTTP operates. And now we're getting to the meat of it. How does actually HTTP operate? So the first thing that HTTP does is, so if you're a client who's using HTTP, you'll ask for a TCP connection. That TCP connection will be acknowledged, and once it's acknowledged, you'll ask for files. Sorry. And when you're asking for the file, you'll also actually specify whether or not to close a TCP connection after this. Yeah. So here's one demonstration. So initially you just have a TCP connection established. This guy, it acknowledges it, it sends back the acknowledgement, some response. This guy's like, okay, cool, now I know that the connection is there, so I'll just send a request for a file, and then this guy, it transmits back the file. So that file is going to have slightly more data, and that's why you require a bit more time over here, right? This is like the time for the file to be there. This initial time, this half round trip time, that's just for the first packet to reach, and this is for the remaining packets to like all reach the computer. So this this time that is required for the round trip is called, of course, the round trip time. So the half of that is basically time required for packets to reach from one end to the other end. Yeah. So here what you are seeing is a classic example of a non-persistent connections where you just have one file being sent for one connection. What if you want many different files? Turns out the best way isn't actually to be sending you know, each file over a separate connection, because then you would have this extra round trip time for just the acknowledgement that the TCP connection is built. Yeah, so whatever it is to do is you use the same TCP connection, don't have the close header, and then send another request, and that will send another file, and so on. That's a persistent connection. So for example, SMTP uses a persistent connection because it sends all the mails on one connection. Now of course you can make this 1,000 times better by asking for all the files, and the device that's supposed to send all these files, sending all of it in a pipeline fashion. That is, the first file is over, okay cool, keep on sending, go to the second file, keep on sending. Don't even care about like whether or not like that file is going to reach. Just keep on sending. That will make all this files reach from B to A much faster because it's all pipeline. So you could also think of it as all the files being combined into a single very large file, and then that file being sent. Yeah, but really if you're thinking it more in terms of the HTTP thing, what actually will happen is, over here when you request a file, you don't even care about that file reaching back. You just straight up start requesting even more. So you'll have a bunch of these requests, and for each request this thing will send back a file. That's what truly pipelining is. It's not just like requesting all the files at the same time, because you can't do that. In HTTP you just can't do that. So you'll have a bunch of requests pipelined. Yeah. Yep. Okay. This is just whatever we discussed previously. So that's HTTP. That's like the first part of chapter 2. Let's go to electronic mail. This is even more complicated. So the three components involved, they are the user agents, which is like the browsers, the mail servers, the browsers or something else, Outlook or whatever you have. Mail servers, which are basically servers, except they operate slightly different from normal HTTP servers. And then you have a simple mail transfer protocol, that's the SMTP protocol that you have. So what's a mail server gonna do? It has two components. One is the mail queue. It's the queue of all the mails to be delivered. And you have a user mailbox, which is all the mails that aren't delivered to a particular person who is connected to this mail server. Yep. Yeah, true. Okay. So here what we're kind of assuming is that everything's static. People aren't like changing their mail servers all so often. Everyone knows everyone else's IP addresses. Of course, that's a very simplified assumption, but let's just assume that that's true. And even then, it's kind of complicated. So you can have a direct server to server. So that's what happens. You have direct server to server connections. You don't have any intermediate or central mail servers. So like in HTTP, you might have this thing where you have like that file isn't there on this server, so it will like get it from some other server or something like that. Right? In DNS, this definitely happens. You do not have you do have central servers or like zones which are bigger, or we'll talk about DNS soon. But in electronic mail, you do not do that. Right? So the two mail servers that are associated with the clients, they communicate directly. And since SMTP is slightly an older protocol than HTTP, it uses a bit of a primitive message format. So you can only have 7-bit ASCII characters. Everything that you have, all your data, it must be encoded as 7-bit ASCII characters. You have an image, convert to a URI first. Okay, just like HTTP, SMTP has a client and server architecture. And of course, you have a client side and a server side for the application. SMTP, that is. Now, the actual protocol. There are three parts. There's SMTP handshake. There's the mails actually going, and then you have a closing section. And these aren't like formal stages. I just came up with it just to keep my head sane. But yeah, let's go over it. SMTP handshake. So first thing first, build a TCP connection. Let's say you have a server, you have a client A and a client B. Okay, I don't know why these are servers. It should be mail clients, user agents actually. No, you know what? Okay, no, this is actually fine because it's supposed to be mail servers, not clients. Okay, I don't know how to exactly explain this thing. These aren't servers, okay? These aren't servers. These are like domains actually. These are host names, in fact. Yeah, so these are hosts, not mail servers. So you have hosts A and B. Like these are host names, by the way. Hamburger.edu, creeps.fr, right? You know, okay, maybe this is kind of wrong. Maybe these are actually mail servers. Yeah. I think these are mail servers. Why else would I have written it there? Okay, so you have mail servers A and B, and they have these names. So mail server A has the host name creeps.fr, and this has the host name hamburger.edu, and A wants to send a bunch of mails to B. So first what happens is A establishes a TCP connection, that is to say A is the client process. Right, now we proceed with the handshake. So before even like going over, I'm just going to tell you the thing. So B first acknowledges that yes, it is available. So it does some like I don't know. Okay, what exactly was the format? Yeah, it just sends this thing. So it just sends a status code 220 and then its own host name, that is hamburger.edu. Then A starts with a greeting. So it does hello and its host name. So it does hello creeps.fr, to which this guy responds with once again a status code, which I think was 315 or something, and then hello creeps.fr, nice to meet you, or pleased to meet you, or something like that. I'm not making this shit up, alright, this really happens. So it's hello creeps.fr, pleased to meet you, not meet you. Yeah, and the status code is 250. So the status codes so far are 220, 250 in the handshake. Now comes the meat of the portion, sending the mails. So this happens using a mail from thing. So what A does is it says mail from this user alice@creeps.fr. So that's once again this is basically an email address, alright. Yeah, so P basically responds to that, and it sends, okay, the sender is fine, that I recognize the sender. So 250, this is the same status code as we saw before. So I think 250 is just like an okay, more or less, and 220 is a ready, I don't know. So 250 alice@creeps.fr, sender is okay. Then you have a recipient, so it's RCPT2 and whoever we are sending to. So in this case it's bob@hamburger.edu. Once again, B checks if the receiver is okay. So it does 250 bob@hamburger.edu, recipient okay. Now we actually start sending the mails. So of course there are going to be like multiple mails, so this will happen many times. But yeah, finally A starts. So that there might be like multiple receivers, so this might happen multiple times. In which case, like, you'll just be sending multiple mails. That's all. Yeah. So now we start to actually send the data. So A basically asserts I'm sending the data section, which B replies send it. 354 enter mail end with dot on a line by itself. Of course, we don't really need to know this, but B sends it anyway. And so 354 is once again just like I'm ready, get the thing. And so A starts doing it. So this is the actual data in clear text. Do you like ketchup? How I don't know, it could be anything. It could be some whatever, some URI. So it sends all that, and then at the end, just as B told it, it sends a dot, just a dot. So this basically specifies that okay, the data section has ended, and to that the B thing replies 250 message accepted for delivery. Yeah. And then you just do the same thing again and again for different for all the mails, in fact, that are supposed to be sent from A to B. Once again, A and B are the servers, the mail servers with their host names. And just so you know, like it's a tidbit, the host name is usually an alias host name. It's not even the real host name, but that's just like unnecessary complex. You just assume that the whole mail system just has one server, right? Just two servers is more like it. I don't know, but yeah, just assume that. Okay, closing SMTP connection. So once all the mails are sent, A can just send a quit and B will reply 221. So this is different. It's 220, 220, 221. In between there was a 354 as well. So 221 hamburger.edu dot closing. I don't know why there's a dot over there. This is supposed to be closing connection. Closing connection. Yeah. And that's it. That's the SMTP protocol. It's verbose, unnecessarily verbose, which is a bunch of weird status codes, but it's fine, I guess. I mean, it works. Okay. Now the mail format. So of course the mail can be any sort of text, right? The data section. But usually in the mail you'll have headers which are mail from and recipient to, just like repeating that in like from and to headers. And you also have some other headers like the subject or the date or something like that. Yeah, so after the headers just leave a blank line and then start the actual body. So this is still inside the data section, except the real body isn't this stuff, it's what comes after this stuff. So this is called peripheral information. Now access protocol, that's another thing of the mailing system. So SMTP is a push protocol, which means that the moment that somebody sends a mail, the mail actually goes to the server instantaneously, and then the server queues it instantaneously, and then it goes to some other server instantaneously, and it sits there, right? It does not actually go instantaneously to the receiver, and that's because the receiver is not always on. So till that point it's a push protocol. From there it has to become a pull protocol. So HTTP is, for example, a pull protocol, where the client, when it becomes online, it will pull stuff from the infrastructure. Over here, when the client is there, it pushes stuff, at least the sender, it pushes stuff into the infrastructure, if that's making any sense. But now on the access end, we still have to have a pull. So how do we do that? There are multiple ways, and the oldest one is called POP3, which is the Post Office Protocol version 3. What this does is, it has its own protocol, but it's actually kind of simple. So there will be plus OK and minus error for each thing that the server is going to send. So for each message the server sends, it's either going to start with plus OK or minus error, depending on what exactly is the, like, how did the execution go. So there's two stages. First is the authorization. So yeah, whoever wants to access, he has to give his passwords and all that. So he'll give user and password fields. So the receiver, he establishes TCP connection, of course, on the mail server on port 110. So that's for POP3, right? You know that actually it's port 25 for SMTP, but over here it's port 110. Now the mail server M, it sends a plus OK POP3 server, it's ready to indicate it's available. B sends the username as user Bob is the username. M responds okay. B sends the password as pass Hungary, so this is just the password. Hungary is the password. M responds okay, user successfully logged on. So that's just the login stage, right? So all that happens is the server will send server ready, the user will send user, the username, server will send OK, and the user will send password, so just pass and the password, and server will respond OK, logged in. Yeah, so if you make a mistake, it will show an error and it might just like reset the whole thing. So it's more or less like a shell, and the actual transaction starts like this. So it's extremely similar to something like SFTP or FTP, because yeah, it's scary similar actually. So the user can do these things. It can do a list, it can do a retrieval, and it can do a deletion. So what list does is that for each mail it indexes it by some number, and it also sends like the size of the mail. So in the mailbox for B, not B, but so here once again B isn't actually the user agent. So B isn't actually the mail server, it's a user agent which I'm talking about. Yeah, so slight confusion between the last section and this section, but here B is the person and not the mail server. So B starts with list and responds with a list of indices for the mails and the sizes. Then B tries to retrieve the mail, sends a retrieve, so retrieve and also the index of the mail that you want to retrieve. Then M will send the data, and it will finish with a dot, right? So every time that you have to send a bunch of lines, you want to end that with a dot. So for example, over here you are sending a bunch of lines, that's what the server is sending, so it has to send a dot. The user, on the other hand, it does not actually send a dot because it is going to be in one line. Yeah. Now it has retrieved it. It can either delete the mail, or you can just leave it like that. And so it retrieves a bunch of different mails and then it just quits. So it does the quit command, and then the mail server responds with OK, server signing off. So there's a log on stage, there's the transaction stage. Now some issues with this, if you have the deletion thing going on, that you just retrieve the thing and you delete it so that the mailbox becomes empty, right? The one big issue with that is that if you have multiple user agents for the same user, they will both have different mailboxes, which is kind of messed up, isn't it? So instead what we could have is just a download and keep sort of paradigm, where the user agent will just download the thing, but it will keep it, like it will keep it in the mail server. So it will only get deleted once the user itself, he wants to delete the thing. Of course, this is heavy on the server because now the server has to store all of that. But yeah, if you want to give that sort of services, that sort of service that the user can have two different devices with the same account, you need something like that. And then there's a slight modification of POP3, which is actually not a slight modification, it's a much bigger modification. And what this thing, so IMAP, what this thing does is actually it provides a folder structure. So now everything initially, so like for each user, its mailbox is a very big folder called the inbox folder. Inside of that you will have subfolders. So what the user can do is that it can create a folder, it can switch files, not files, it can switch mails from one folder to the other folder and so on. It can delete, of course, and it can read the thing and do all that. Yeah, so this allows for things like Gmail. Also it can actually like just have parts of the mails of the mail read rather than the full thing. So you can have things like Gmail happening. So yeah, IMAP is what you really need to have something like Gmail built, but then in reality Gmail is built on HTTP. So rather than using these access protocols, you could just use HTTP, right? Think of the mail server as just a server and communicate with it directly using HTTP. So nowadays everything's moving to HTTP. Even so sure, between the mail servers is still SMTP, but the clients communicate to the server directly using HTTP. So HTTP can work both for pushing and pulling, although usually it's just pulling. So the Alice person who wants to send a mail, she can use HTTP to connect to the first mail server. The mail server uses SMTP to send it to the second mail server, and then Bob on his end, he uses HTTP to get the data or get the mail from his mail server, right? And now coming to the most interesting section, that is DNS. And frankly, when I read this is like, I just have to appreciate the complexity. Like, okay, SMTP, HTTP, these are there. It's like simple protocols which anyone could have built. This thing, it's messed up. There's just so many moving parts. But okay, let's do it. So DNS is domain namespace. It's a very important application layer protocol. So it runs usually on TCP or UDP, mostly UDP. And what it does is that if you have the host name of some host, it will figure out the IP address for that. And do remember that you need the IP address to connect through HTTP or through SMTP or even just a TCP connection to anything in this world, right? So you need to know the IP address, but then you don't actually use the IP addresses. When you say like google.com, you don't know the IP address of the server that you're connecting to. All you know is google.com, that's the host name. So that's what DNS does. It figures out the IP address, right? So what does it do? It does a mapping. So which layer does this belong to? You might be tempted to think, okay, if this is required for the TCP connection to be built in, it should probably be a lower layer than TCP. No, it uses TCP connections, already existing TCP connections, and the already known IP addresses to the DNS servers to figure out more IP addresses of hosts which you want to connect to using TCP. So it is still an application layer protocol. Yeah. Network architecture, okay, this is where the complexity starts. So you have many DNS servers running at different places. The servers usually are Unix servers. They use the Bind software, Berkeley Internet Name Domain software. And your ISP, it usually has the IP address of the closest DNS server. So when you log on to your Wi-Fi, right, you are actually using, so when you like do a Google search or go to some host, you're actually using the DNS server that your ISP is connected to actually figure out what the IP address is. And this might even reach all the way to your like device level, where the device might create IP addresses itself, or your device might be hard coded with some of the IP addresses. So there's that. You have usage overview. So DNS is so like, okay, DNS uses port 53. So just to recap, so POP3, it uses port 110, SMTP uses port 25, HTTP uses port 80, and DNS uses port 53. So when a client wants to send their IP address associated with a host name, it sends an inquiry to the nearest DNS server. The query is eventually answered, and then the client proceeds with creating a TCP connection. That's just like a high-level overview of what happens. Now, how does this happen is actually the question. First, let's just figure out about the nature of mapping. How are the host names, they're mapped to the IP addresses. So you already know that inside of a institutional network, you have these MAC addresses, right, which are associated with the machine itself and not to the actual IP address, like the IPv4 thing. Well, that's the sort of mapping that I'm talking about. Like, what's the nature of the mapping? So in this case, the mapping it's not injective, it's not even a function, this is just straight up a relation. So you can have multiple host names having the same IP address, that's called aliasing. Okay, the aliasing is slightly more complicated than that, but you could literally have like multiple host names having the same IP address, right? Or you could have the same host name for a bunch of servers all having the same IP address. So yeah, it's like a relation. Okay, that's the nature of mapping. Now let's think about how this actually happens. So first thing is called host aliasing. So if a host name for a server is rather complicated, it might be beneficial to replace with a simpler host name. So the most cheap way of doing this is basically having a record in the DNS servers that, okay, I'm also going to use this other host name for everything. So that other host name is called an alias, and this alias actually maps, points is more like it, to the canonical host name, the original host name. And the canonical host name, it points the IP address. So yes, there's a bunch of weird shit going on over here. Like you have linked lists and pointers and who knows what's going on. But really, when you actually look at how it's stored in a DNS file, it's more like a database and not this complicated thing that you're thinking of. Okay, so this thing is important for something like a mail server, where you have multiple mail servers, each with the actual host name. But then when you say gmail.com, you just get a mail server. You don't even have to worry about what mail server we're talking about, because how do you even do that? Like, what server is gmail.com? Turns out it's all of the servers, because all of them have an alias name gmail.com. That's making sense? When you say gmail.com, what DNS actually does is that it picks any one of these servers and then returns that to you. I mean, returns not the canonical name, but like its IP address to you. Sometimes it might even return the canonical name. So we'll get into that when we read about the message format. Okay, so when you want to connect to any mail server for a mail application, you of course want to know its actual host name. Instead, what you'll know is the alias name, which is the same as all the mail servers, which are virtual. Okay, for example. Right, and that's just host aliasing. There's load distribution. Here what happens is that you might have different mails, you might have different servers for the same application, right? In like a game or something, you might have like multiple servers all running the same game. What you would want to do is that whenever somebody goes and like types in your alias as the host name, you want to return one of these servers, but not the ones which are busy. So you want to distribute the load over that, and we all know that the best way to distribute load is using a round robin mechanism. So what happens is that the DNS server, it says, okay, I'll give you whatever the first hit is, but then once I do that, I'll actually rotate the full thing. So it literally like rotates the list that you have for the same host name. Yeah, I mean the mapping for hosting to canonical hosting thing. Yeah. Okay, how does DNS actually work? So yeah, this is gonna get very complicated. Yeah, you know, maybe this is like one of those things where just me telling how it works isn't going to be enough at all. You'll probably have to read through all that. My god, I really wonder, how do people even teach all this in so little amount of time? Yeah, you have a bunch of things that you'll have to read through, because this just isn't something that I'm going to be able to do in a rational length of this video. But yeah, that's like a high level view of what DNS is. Okay, I haven't even like touched you know, all these like resource records and all the different ways that a DNS server can query, recursive, iterative. I haven't touched like the hierarchy of DNS servers. I haven't touched a lot of things, frankly. Yeah, all I need you to know is that this is like this is slowly going to get more and more complicated as we go on. So at some point I'm just going to be able to give you high level overviews. So now I'm going to drink some water, take maybe a break. Right, you know what, let's actually make this a two-part thing, where I just do this video first and then I'm going to do the second video later. Yeah, so that my throat isn't going to just, yeah. Okay, I'll see you guys in the next video.